Hello everyone, welcome to Fermat's last theorem for beginners. That sounds like a contradiction. Brought to you by Variety and Fun Math and Martin Tutorials. What a name for a video. Fermat's last theorem for beginners. That sounds like a contradiction. I intentionally put in that second line in the name because it sure sounds like a contradiction. It's like me saying this course is called Driving a Sports Racing Car for First-Time Drivers, or PhD Nuclear Physics for elementary students. But there's a good reason for that contradiction. The reason is because the theorem itself is very easy to understand. The proof, however, is about 200 pages long with very advanced, sophisticated mathematics. And this paradox, an easy theorem with an advanced proof, that's what intrigued me to make a video. And where I am going to open the cards with you, I do have notes prepared on the side. So every so often you'll see my eyes turning to the side. It might seem a bit impolite when the camera's here, but I don't have this unbelievable memory. I have to keep notes. And as I said, this paradox is what intrigued me to make this video. And this lesson is about what the theorem says, a brief history, but thankfully for both you and me, it's not about that 200-page proof. Okay. Fermat's last theorem was formulated by a mathematician called Pierre de Fermat, or Fermat. Someone who speaks French would pronounce it right. I apologize if I pronounce it wrong. Who lived from 1607 to 1665. Around 1637, Fermat wrote notes about his theorem. He took another math text called Arithmetica, which was by a mathematician called Diophantus, and I hope I pronounced that right. I apologize if I didn't. Diophantus lived many years before, and he produced this text called Arithmetica, and in the margins of that text, that's where Fermat wrote his theorem and all about his theorem. Okay. I will now proceed to explain what this theorem states, because that's what I said I will do. Okay, in front of us is a piece of paper with some equations. To begin with, I'm going to concentrate on this one here. A squared plus B squared equals C squared. All right? Now, the question is, can we find numbers that make this equation true where A, B, and C must all be integers? I'll show you what I mean by integers. There's integers like 1, 2, 3, 4, 5. Root 9 is also an integer because root 9 is 3. It's like 74 is an integer. And here are numbers that are not integers. Root 3 or root 5, because root 3 in decimal is 1 point and are endless decimal points. So integers are specific numbers like 8, 11, 12, etc. So this A squared plus B squared plus C squared, can we put numbers in where all three numbers are integers? Now, also I said those integers must not be 0. Otherwise it's easy. Here we go. 0 squared plus 0 squared equals 0 squared. And here's another one. 9 squared plus 0 squared equals 9 squared. So once there's zeros, it's easy to do. 0 squared plus 4 squared equals 4 squared. So they have to be integers and not 0. And you will see it's actually not that easy. Like, let's say you make up a number. Let A be this and let B be that. What is C? So I'll just make it up. Let's say I say A equals 4 and B equals 5. I do the arithmetic. C is root 41. If I say let B equal 7 and C equal 9, I do the arithmetic. A will be root 32. So you will see that it's not easy to find the right integers. But notice my wording. I said not easy. I did not say impossible. the numbers do exist. Here's one perfect example. 3 squared plus 4 squared equals 5 squared. I believe that's one of the most famous ones. You can check that with a calculator. And here's one more. 5 squared plus 12 squared equals 13 squared. Check with a calculator, you will see that is also true. Okay. But here's an interesting question. What about a to the 3 plus b to the 3 equals c to the 3? Or a to the 4 plus b to the 4 equals c to the 4? Or what about a to the 20 plus b to the 20 equals c to the 20? Can we find integer solutions other than 0 that will work in that? We will always find irrational numbers but actual numbers like 1.337 or something, but proper integers to fit in if that exponent, what we pound to, is bigger than 2. Okay? And what Fermat said in his theorem, that it's absolutely impossible. He said if you want to try put the integers in for, let's say, a to 3 plus b to 3 equals c to the 3, it's not that it's difficult or it's going to be much, much harder. It's absolutely impossible. They do not exist for any number with the exponent that's on top bigger than 2. It is possible with 2. I just showed you 2 examples. But the power of 3 or the power of 4 or the power of 5 or the power of anything like a to the 11 plus b to the 11 equals c to the 11 with only integers fitting in, Fermat says there is no answer. Not that it's harder to find, but they do not exist. That means you can try this out a million times. Let's say a to 3 plus b to the 3 equals c to the 3. You plug in integers for a and b to look for the c. You try that a billion times. Try this and that number, that and that number a billion times. You will never find an integer answer for c. And that's what Fermat's last theorem states, that if that exponent, that number you're prowling by, is bigger than 2, it's 3 or up, there absolutely is no answer. Not that it's very hard to find, it does not exist. Okay? And this theorem was made known to the world after his death. His son, and again, I hope I pronounce his name right, his son's name was Clément Samuel Fermat. He found his notes in that text, and Fermat's son published them in 1670 together with the text by Diophantus called Arithmetica. That's when the Fermat theorem became official. Okay, Fermat claimed he had a general proof. The actual proof, proper proof by Fermat was never found. It is possible that he did have a proof, it's just we haven't found it. So now it actually became a big deal among mathematicians to either maybe find that proof by Fermat or create your own proof. And over centuries, many mathematicians tried to prove Fermat's last theorem. And try as they might, they never managed. Many were nearly there, but then they found flaws in it. Okay. Eventually, there was a professor called Andrew Wiles, a math professor at Oxford, and he found a proof. He worked for it in secret for 7 years. He presented the proof, and then they found some flaw in it, and he spent approximately another year with a former student of his perfecting that flaw. And in 1994, Professor Andrew Wiles had that proper proof for the Fermat's last theorem. That proof is approximately 200 pages long with very advanced mathematics, and they use 200 pages. They use the words approximately 200 pages because they say it depends on the paper, the size, how you're writing the paper, and there's some supplementary material that is or isn't sometimes included, but nearly all experts agree that saying 200 pages is a fair approximation. And most mathematicians also agree that if Fermat did in fact have a proof, it would be totally different to Wiles' proof, because Wiles used math techniques that were not available during Fermat's time. Think about it. 200 pages, about 200 pages, to show that a to the 3 plus b to the 3 equals c to the 3 does not have a solution. Okay? Simply put, it is an easy theorem with a complex proof. As I said at the beginning, this video is about the theorem, what the theorem claims, and the brief history. I'm not making a video analyzing that 200-page proof. If any of you viewers want to make that proof or create a video, please let me know. I'm happy to watch. And in conclusion, just for your interest, I'm going to show you this beautiful chart. This chart shows examples of numbers where a squared plus b squared equals c squared, where it's integers and not zero. As one example, 8 squared plus 15 squared equals 17 squared, or 39 squared plus 80 squared equals 89 squared, etc. So that's just a chart with some of them at random for you to look at. While you're looking at this chart, I want to mention that if any of you can produce a chart similar to mine for non-zero integer solutions for a to the 3 plus b to the 3 equals c to the 3, or a to the 4 plus b to the 4 equals c to the 4, for example, please let me know. I would love to see that chart. It would not only be interesting, but you would be very famous, extremely famous. That would contradict Fermat. As we have seen, mathematics is full of surprises and challenges, even occasional humor. While Fermat's last theorem may be daunting, remember that every discovery starts with a simple question. My suggestion to everyone is keep asking and exploring, and who knows, maybe you will have a breakthrough. It might be mathematical, it might be another field. So if you enjoyed this journey, please keep watching my presentations. Please also advise me if there's any topic you'd love me to cover or talk about. Put in the comments section you want me to give a presentation on this topic, or have a question about this math question, etc. And if it requires more difficult math, it would go on to my other YouTube called Martin Tutorials. Thank you all for watching. I appreciate it, and I hope to see you all again soon. Take care.